Alright everyone, I'm going to go ahead and get started. If you remember at the beginning of class, I had everyone kind of mess with VirtualBox for a couple of examples. This will start the part of the class that's going to be a lot more focused on actually using VirtualBox to work with malware that's executing. So generally describe that as dynamic analysis. The analysis we've done up to this point is what I traditionally would call static analysis. Or if you want to think about it this way, we analyzed malware at rest before, now we're going to analyze live malware. So we will talk, especially later on, about, so in the next lecture I'll have some demonstrations about, or I should just say, I'll talk to ways to, not shoot yourself in the foot, that type of stuff. So ways to safely analyze malware. We'll also talk about a large number of tools, because this is also the one where you'll be dealing with a lot more kind of tools, especially ones that were designed for Windows and things like that, that are going to be monitoring malware, and less with say, stuff that you can write yourself. So we will also discuss runtime debugging. Oh, is that not locked? Or, I mean, is it locked? No. Okay. So we'll also discuss runtime debugging, which is, you saw we used the disassemblers, and we use IDA Pro, or I should say we used IDA Free to look at malware and look at the code and everything. We actually did some runtime debugging examples when we were playing around with GDB. So it's also feasible, and there's a number of debuggers out there to do it in Windows too. And so we will go into all that. So this class, I'm going to focus on this lecture. The next class I'll be having probably no slides or very little slides and a lot more kind of hands-on demo. So it'll be similar to the rhythm of similar to what I did last week, I believe. So, so getting into it, I kind of like to think about this first in terms of static analysis limitations. So it's, setting up VirtualBox, working with it, that type of stuff, definitely can be more cumbersome. It takes a little bit of infrastructure to get working. So I always like to try and think about, why am I not just trying to solve the problem with static analysis? So wrote some content here, but one of the big things is just that static analysis can be very time consuming, trying to figure out what a program may be intending to do and everything like that. If you're not running it, requires analyzing the code, analyzing the assembly language to figure out exactly what sequence of steps it's trying to do. As any of you can relate to, that can be a very time-consuming process, and generally when you're dealing with attacks, you're dealing with the need for answers in a much shorter span of time. Another aspect is that there are changes that are affected on the systems that are compromised, and you basically want to be able to see those changes and determine if you can monitor for them or if you can search for them, that type of stuff. So for all those reasons, I kind of say that static analysis has its limitations. We try and fill in those gaps as much as possible with dynamic analysis. The flip side of that coin is that dynamic analysis, you can really only extract the behaviors and everything that are in a limited feature set of what the malware can do. You're frequently not dealing with something that you have the source code for, or that you have like a control system for. So if you think of one of those backdoors that we had, like Metasploit, for instance, had that metarpreter payload that it delivered, and that what you were doing was you were actually interacting. You had control over both sides. You had control over the client or the target, and you also had control over the server, the computer that you were running Metasploit on. Most of the time when you're dealing with malware infections, you really only have the piece that they're delivering to targets. You don't have that controller piece. So therefore you don't have all the knobs and all the buttons and everything like that to play with. So that tends to be where static analysis does come in to be beneficial, where static analysis can give you a more comprehensive look at what the malware is capable of, but it takes a lot longer to find any individual piece. Dynamic analysis can give you a narrow focus of, say, by default, what does the malware do when it's first run on a system, or when it's left running for a little while, but it doesn't give you the visibility into everything that it can do normally when you're dealing with it. So that's why we do both of these. We don't tend to rely upon one over the other or anything like that. So I'm going to short slide here about runtime analysis, basically, and I mentioned this earlier, involves kicking off the attack inside a controlled environment. Sometimes they describe it as detonation, because a lot of people like to think of malware in terms of weapons, because, I mean, everyone has their preference, metaphors, that type of stuff. Some people like to think of it in terms of warfare and weapons. Some people like to think of it in terms of sports or competition, like that type of stuff. Pick your poison. But I'll say that there's two common approaches to doing this. The one that you'll be familiar with here is going to be the first one, using VM, hypervisor, or emulation. And primarily we're going to deal with the hypervisor, so we're not going to do too much emulation. The difference between those is, those of you who are in the cloud computing class are aware, hypervisor means that the malware's instructions are executed by your processor. Emulation means that the malware's instructions are interpreted, and then a separate set of instructions are executed by your processor in response to that. So emulation definitely gives you a larger kind of separation between malware and processor, but not a lot of speed. And then finally, actually the one that is probably most effective at getting the getting the results that you want is what I call bare metal, which is actually not uncommon for places that have resources to spend on it. And a lot of malware research firms will do this. So you're familiar with a lot of different companies that do malware research. They'll actually set up labs, so racks with a lot of different machines in them, a lot of different configurations. And they'll have closed physical networks and everything like that to do malware analysis. I wish we had that here. We don't, because that would actually be a very beneficial addition to this course. Maybe some point in the future we will. So in observance of the limited financial resources that all of us have here and the university has, we're just going to be focusing on using, I'm going to be using VirtualBox. I do not mind, as I've mentioned before. If any of you want to use any other virtual machine systems that you have a preference for, you may even use, some of the online, like cloud services, that type of stuff, the infrastructure as a service things. I would just caution you that if you are trying to use any of those things to do runtime analysis, make sure that you read the user agreements that they have, because some of them might actually have rules against using them for analyzing malware, or they at least might turn off your VM or something like that, and you might not be aware that they're actually doing that type of inspection. So next piece that I'll talk about is I like to think of what the attacker is trying to go after, or is trying to access, or is trying to hit as the attack surface. So I'll call this the runtime attack surface. And I like to think of it that way just because it's it's like something that you want coverage on. So much of your surface is, say, vulnerable to certain attacks, that type of thing. Calling it attack surface kind of gives it that model of being able to, determine how much of it is covered versus not, that type of thing. So it gives you some sort of like kind of quantitative perspective on that. So anyway, so I use the term attack surface. I'll use it in the future, and that's generally what I'm referring to. I tend to carve it up. Again, this is just the runtime stuff, so not necessarily network infrastructure and things like that. But when we're talking about running or delivering malware to a target, we're talking about trying to get executable code onto a person's system so that you can go and perform X operations after that, so you can achieve some goals. I like to carve up that attack surface that exists on, say, every person's computer or every server, that type of thing, into these like 6 buckets. The reason I do this is because a lot of times I'll end up using many different tools to try and get information out of a system that I'm analyzing. And also, when I'm dealing with a network that has a lot of systems on it, I need to be able to manage how I'm doing monitoring, like active live monitoring of all those systems. So breaking up the attack surface into these bins means that I almost have a checklist, or at least a short list of places that I'm going to look for activity. So I put in these 6, like file system changes, paths, directories, that type of stuff, and file content. The execution environment, the place where programs are going to try and execute their code. Operating system and user configurations. So I installed Linux on this laptop, for instance. I installed one specific version or distribution of Linux. Any of you may install, say, another one, say Mint or something like that. The configuration of that and layout's going to be different. It's going to expose its own like nuances and vulnerabilities that's going to be different than what I have on mine, even though they're both the Linux operating system under the hood. Persistence mechanisms. So we generally think of a long-term intrusion by using the term persistence, which is the attacker able to maintain connectivity, maintain access across, say, reboots and things like that? How do they do it? How do they achieve long-term access to the network? System and user object resources. So every single computer has a number of resources that the operating system is managing. And then finally, network. How is that system that was targeted, how is that actually getting access to the internet? How's it getting access to the rest of the private network? How's it getting access to the home network of the user, for instance? How's it getting remote access? All those things. So if an attacker basically is running a program on my computer, unbeknownst to me, these are the places that I'm going to try and search conceptually to try and see if I can find any evidence of that running. So file system modifications. So that was the first bullet point. So I'm going to go through a number of these. But in many cases, those of you who've taken like the operating systems course might be familiar with this. But those who haven't might remember when we were going through the XREF table, or the objects listing in PDF documents, and we were also going through the FAT, the file allocation table that was inside of the Microsoft CFB file format, and that described subcomponents or streams within the document and gave them names and gave them identifiers and things like that. So your file system basically has a directory of all these things that's almost like an index or table of contents, whichever one you want to think of it as, that tells your operating system where the, or I should say it connects the names, so the long file path names, things like that, to all the data streams that back them up. So as you can imagine, anyone who's trying to do or perform actions on your system very likely is going to end up making modifications to this, to these data structures while they are, say, copying files, deleting files, moving files, all sorts of stuff. When any of you are using your systems, you're constantly making changes to this directory structure. So, very commonly the attack chain involves multiple actions that will expose an intrusion on the file system. So an example might be, and I gave a like 8-step example here, which is say you know, I get an email, it's like a phishing email. Email tells me to click on this link to go and view a purchase order that I have that's supposed to be sent to me. It's a fake purchase order. So I'll click on the link, Internet Explorer opens, then it downloads this bad.pdf. Normally, if you're using Internet Explorer, that'll get downloaded either into the downloads folder, or it might get downloaded into the temporary internet items folder. It depends on your configuration. So what that ends up doing is that creates a new record on your file system that didn't previously exist. So that creates a new file name on there that didn't exist, and then it also allocates storage for that. Then what happens is the user opens that PDF. So after it's written to disk, the user opens it, which then causes another entry to be put in the file system, which is the access time, which is going to be different from this creation time. And the access time tells you when, say, that PDF was opened. Then bad PDF gets read by Acrobat Reader. It exploits Acrobat Reader. And once the attacker's shellcode successfully gains control using one of the techniques that we discussed last week, it performs two actions. Immediately it writes good.pdf to disk, and then it also writes bad.exe to disk. And it may write them into a folder that's represented by this temp environment variable, which is a common environment variable that's available on all your Windows systems. So you have anytime a program wants to temporarily write a file to disk, there's actually a folder in Windows that's designed for that. And it also ends up being a common place where malware writes stuff to disk. So these two files get written to disk there. Then the next step is the attacker shellcode opens both of those. So it uses a WinAPI shell call. And WinAPI is basically operating system or library function provided by Windows. So it's a C function provided by Windows that allows Windows to just open either one of these. And what Windows will do in response to that is it will look inside the system configuration. So I mentioned up here that there's operating system and user configuration. If you've ever downloaded a file from the internet and tried to open it, sometimes it'll actually prompt you, if it doesn't by default have an application associated with reading that file format, it'll prompt you to select one from the list, that type of thing. That's actually something that's stored there so that the attacker shellcode could run a function that basically opens each one of these files with the standard, or I should say the default application. So after that happens, bad.exe, so it opens both of those. They're running in parallel. So good.pdf loads up Acrobat Reader. Bad.exe also runs in the background. And bad.exe might go and delete bad.pdf. It knows that bad.pdf is there. It might go and delete it. So you've got creation times for both of these files now in the directory. You've also got access times. And now you've got a deletion time. And we'll go into this in a little bit more detail, but one of the interesting things about Windows file system, and some others, but we primarily deal with Windows a lot of times, is that when you delete a file, the file's not immediately deleted. Actually, that file entry and even the data that was for that file that backed it, that actually remains on your system. So it remains resident on the system, both because it's a lot quicker just to turn that file off in the file system directory than it is for it to actually go and write zeros all over it. So it saves time, but also it makes the file recoverable. So if you decide like, oh, I want to delete it, but then you're like, oh, actually I didn't want to delete it, it allows you to use one of the recovery tools that actually exist. So a lot of times an attacker may try and delete a file, but if you do analysis with one of the tools that we'll talk about on Thursday, you can actually see that show up. So that's why it's noted here as another action that occurs. And then bad.exe may write a what's called a symbolic link, or a shortcut in Windows, which in the Windows drop-down menu actually uses the term shortcut. So it may create a new file that's a link file in your startup folder in your start menu, so that it can be loaded next time you log in. And that might refer to this bad.exe. And then bad.exe establishes a communication link with an external, what we call a command and control server. So bad.exe, in the end, after I've kind of looked through this chain of events, and I was able to put this story together, I could determine that bad.exe was probably a backdoor of some sort after I realized that it did all these things and then also established a communication link with an external command and control server, so an IP address or domain name that was hard-coded into it, it tries to connect out to, so that whoever's at that end can then remotely control the compromised system. So, yeah. And then I'll just kind of give like a short blurb here. You know, the reason I'm kind of looking at this is that the sequence of events that occurs here is stuff that is tracked by the file system. So it may not necessarily be tracked by the just by the contents of files on disk, but there's actually a number of choices of file names that were made here and locations to install the files in and things like that that also are noteworthy. And may not necessarily be something that can be picked up just by analyzing an individual file using static analysis. Once I learn these things from analyzing how a file behaves, then I can go and hypothetically search for a lot of these things on other systems in my network. So another term that I use is called execution environment. And this one is describing the part of the system where execution occurs. So not necessarily just where data is stored, but also where data and how data needs to live or reside in order to be accessible to the CPU. So I'll lump the three pieces, the CPU, so central processing unit, system memory, and swap memory, into this category. So this is one area that you can search. Virtual machines and even emulation is extremely useful for monitoring the CPU itself. And there's a lot of systems out there that actually employ some level of emulation to try and give you that visibility. But also, what's more common is what's called memory forensics and memory analysis and memory monitoring even. That'll take opportunities to analyze your system memory to try and see if say any program or anything malicious is happening there. The antivirus programs that you use on your systems are a common example of this. So I also talked through some, briefly talked through some obfuscation techniques earlier. I'll definitely be introducing some more examples of that in the slides, but we definitely talked through like the no-op sleds and some of the different encryption techniques that occur. A really good example was how that one exe was embedded in memory when I got to a certain part of the document, and I was able to show that it was just kind of left up to actually unraveling that encryption. So a lot of times the obfuscation techniques that are used for embedding programs inside of documents, things like that, they're also very commonly used just for hiding code. So you can have those types of concealment mechanisms inside of a program that's living on disk, so that, you know, if you're trying to look for a malicious signature or something like that on the file system itself, it's hidden from you and it's only available in memory. So having the ability to analyze memory and see what is unique about the program when it's running in memory is very helpful. One of the key things to keep in mind is that in order for the processor to properly execute the instructions you have, that stream of instructions needs to be decrypted in memory at some point in time. The processor itself doesn't have any inherent ability to do any kind of on-the-fly decryption. So you actually need to have software code that is decrypting either your whole program or at least large segments of your program at runtime. So there's a number of tools like debuggers that allow you to, and we did an example of it with GDB, but we'll do some more with some of the more visual ones that allow you to step through execution. So I can actually set a breakpoint or set a pause point. So my program run up to a certain point and then have it pause, and then I can go and collect all the memory as it is at that state and save it to disk, and then I can let it run some more, and then I can take another snapshot of memory, and I can keep doing this over and over again until I collect a bunch of different snapshots of memory. So analyzing, say, multiple different snapshots from different points in the timeline can also be very beneficial as well as an analysis technique. So the next one we'll talk about is most normal systems that are complex, like this one and yours, so the Mac, Linux, Windows systems, servers, everything. They're usually configured to work under a decently high level of security. It's usually the out-of-the-box behavior. Most of the time when an adversary gets some sort of access, it's not very uncommon for them to attempt to reconfigure a system so it'll operate at a reduced level of security. This allows them to bring maybe tools in that have a lot more power and flexibility to them, and maybe are a lot more familiar for the adversary to use, but may have been tools that either were prevented or were detectable with some of the heightened security the system came configured with out of the box. So it's really common is once an attacker gains some sort of access, they go and look around the system and inspect it with whatever limited access they have or with whatever limited features they have. And then using your, since they're impersonating you basically, they'll use your access to go in and try and turn a lot of the security levers off or try and figure out how they can bypass some of it. And that'll basically make your system be different from how it was originally set up to be or how it was intended to be. So in a lot of environments where you have computers that are managed centrally or managed by like a central IT shop, you actually have an opportunity there to be able to look for things that are out of the ordinary, differences in the environment, that type of stuff. So being cognizant of what a normal working systems configuration is, and then seeing what changes are made by different pieces of malware can help identify this to you. So some examples of configuration changes that might be employed. Many of you worked at moderately large companies or anything like that, or even kind of more tech-savvy smaller companies might be familiar with the concept of using a filtering proxy. For some of you, this is actually a common thing at some schools and everything too, is to basically have a proxy that restricts and filters your access to the internet. So in a lot of cases, if you change the configuration of that on your system, you can get it to bypass the filters that are on there and maybe allow the system to download other stuff that was blocked, and then also possibly, if that proxy exists in order to monitor traffic, possibly make it so that the compromised endpoint or compromised system can't be monitored anymore. Additionally, those of you who've gone and made changes on a system, so for instance, like if I go and install more packages on here, generally asks me to enter my password. That user authentication check, so what level, what frequency of validation is needed, all those things, that also is something that's configurable. Whether like you need to just click OK or cancel versus whether you need to enter your password and enter OK, or whether you're even asked at all. that is called a user authentication check or user acceptance check in some cases. That's all configurable on the system. Event logging, so most of your systems, they're logging various activity that's going on in the background of the operating system every single day. You can change what's logged and what's not logged, that type of stuff. That configuration is something that is, an attacker will go after. So if they want to go and perform a bunch of actions on a system that they don't want to, they don't want to be detected, then they can go in there and change that around. So looking for that type of stuff too, seeing how those changes occur. That's also another route that they'll go. And then service changes, so turning on services or turning off certain services, like a good example might be turning off your antivirus service. That might be a configuration change that occurs, or even turning on remote access. So like even on your Windows systems today, Telnet is so Telnet to your Windows system is still an acceptable service, one that exists that you can turn on if you want. Nobody turns it on, but an adversary may want to turn it on themselves. So Windows contains a database called the System Registry or the Windows Registry. There's a large number of tools out there that actually are designed to provide inspection and visibility of it to you as an analyst. That's pretty much where most system configuration, state information, stuff like that is managed in a Windows environment. That's somewhat out of the ordinary when you compare it to other systems, say Mac and even a lot of Linux systems, which tend to just store that information on the file system along with all the other data. There is a data file on Windows that contains all this information, but generally speaking, in Windows, it's considered to be a live, always-on database that's running in the background as its own service. Because of that, because of the nature of that, it actually has a large number of dedicated tools just for analyzing that. So, see, a subset of configuration is called persistence mechanisms, and this is used to solve the problem. I kind of spoke about it earlier. One of the problems you run into is if you do get remote access to a machine, so that Metasploit attack that we did back in week 2 is a really good example of this problem. If I've got that remote shell and I'm sitting there interacting, if the user just decides like, oh hey, I'm going to close my laptop and go to lunch for 2 hours, then when they come back from lunch and open their laptop again, the connection's been severed and my shell just, or I should say, Metasploit quit. And so there's a concept called persistence mechanisms, which is how do I get my connection to reconnect, or the backdoor to reconnect if the connection's dropped, or if the system gets rebooted, or even in some extreme cases if the system gets re-imaged. So if I reinstall Windows on here, hypothetically, reinstallation of Windows, I want to eliminate anything that I might have added after Windows and basically go back to a vanilla system. So some common methods for persistence include linking or copying malware in the startup folder in the start menu. This actually isn't used by most legitimate programs anymore, so I wouldn't be surprised if anyone hasn't really seen this before, but there's a startup folder in your start menu on Windows. If you put a program in there or a document in there, then it automatically loads that whenever you log in, or whenever you boot up your computer if it auto logs in. The more traditional way of starting up a program or starting up a service when you turn your computer on is registry entries. So that registry database I mentioned up here actually has configuration data that can tell it to run a program or run 5 programs or something like that whenever a user logs in or whenever the computer is powered on. You can also hijack or create a service. So I mentioned earlier that you can run like Telnet as a service in the background. You can run a web server on most of your Windows systems, even the desktop Windows. You can run a web server on it if you install it. You run MySQL on there, that type of stuff as a service. It's not uncommon for malware to basically create its own service and run it as that and give it some name like, remote access system or, runtime health service or something like that, something that sounds nice, but it's actually malware. Another common thing is a hijack a service. So I mentioned on Windows that there are a lot of services that come shipped with Windows that aren't turned on by default. And so Telnet is one of these. It's not uncommon for a piece of malware to go in there and try and see, is there an existing service that's installed but disabled? And if you open up the services menu in Windows, you'll actually see a whole bunch of these that are available that are turned off. What is a lot more effective mechanism for them to gain access is to just replace the program paths and things like that in an existing service that's disabled and then enable it, because it's something that's a lot harder to look for. It's a lot less unique in the environment. Another one is replacing or hijacking common runtime libraries or DLLs to load malware. So there's a lot of common DLLs. We browsed through a folder, I think during one of the hacking examples during week 2, where we looked at all the DLLs that were there. There's a whole bunch of them there that provide all sorts of library code. And a lot of them are used by almost every Windows program. So if you can somehow get access that writes to one of them or overloads one of them, then you can also gain persistence that way. It means that every time the user opens Microsoft Office, it kicks your backdoor off again. Then finally, scheduled tasks. So in addition to services that are constantly running things, sometimes somebody wants a program to run once every weekend or once every night or something like that, to just go. A really common reason for this is to do regular cleanup tasks. So if I was to go back up here, and I mentioned that there's this temporary folder that anytime you have a program in Windows that says, I need to temporarily create a file to put data in, it's extremely common for programs to do that and then never go back and delete that file. So as you can imagine, this folder fills up with a whole bunch of junk regularly. So a common scheduled task solution that most people will use is making a really short script or program that actually goes into that folder and deletes whatever's in there that's more than a week old. So every week, go in there and delete anything that's more than a week old. That way, I'm guaranteed to be deleting stuff I probably don't need anymore, and that's probably not open. So the idea basically is that I set a calendar appointment for my program or for my computer to run something arbitrary, whatever I want it to run, which means an attacker that's gained access to my system could then subvert that to go and run whatever they want to run. And so a really common thing is backdoor still running? If not, then run it. And then maybe have that be a scheduled task that runs every hour or something. So replication methods also can kind of be considered a persistence mechanism. When I say replication, things like, if I want to write malware to a USB drive when it's plugged in and things like that, that's a really good way of maintaining access within a network without, or I should say across even system reinstalls and reimages. Is making sure that anytime somebody plugs a removable disk into the system, that malware gets written to it. So, I'll just go back to the persistence mechanisms. There's one more point I wanted to hit with this, which is even though you can generally look at a lot of this stuff as being changes in the registries, you can use a registry viewer, registry analysis tool to try and give you insight into it. Or in some cases, like this one right here, it's actually modifying the file system. It's writing a new file on the disk. And you can look at it that way. because this is a really common use case that most malware wants to achieve, there's actually a lot of dedicated tools for analyzing this stuff too. So network traffic is another thing. So once an adversary gains access to my system, generally they want to be able to use it to pull data off my system and send it across the internet to their server, or they want to be able to send interactive commands back and forth to try and control my computer to go and take actions within, inside this private network, using the communication channel that was set up. So because of that, most malware has some sort of network protocol built into it. Most of the time, the functionality I've described, so the stuff, if we go back to the list of behaviors and everything that I had, I think in week 3 or something like that, where we started to do the malware classification and what its objectives are and what features it provides and things like that. A lot of that functionality isn't traditionally implemented as part of standard network protocols. Most of its features that are very unique to systems or applications that want to do or provide remote access or provide data theft or something like that. So another thing is that also malware tends to also employ, say, proprietary means to conceal itself, which means that it wants to, it has to operate, in a monitored channel. It wants to create traffic that's not extremely identifiable, but still gets through the network. For these reasons, it's really common for malware to provide basically very unique remote access protocols. Sometimes so unique that they're not extremely predictable. In some cases, they're implemented over like an existing standard, so you'll have it encapsulated within HTTP or a handful of other protocols sometimes. Other times, especially where like the proxy is able to be bypassed or something like that, and they're able to directly connect out to the internet. An example of that, I think, would be like the network we're using now. Then binary traffic protocols that are entirely unique to the malware, so without some sort of like standard layer encapsulation may be used. And so I gave the ghost malware, where this is a 0, is a really good example of one to look at, because it's been around since, I don't know, since like 2005 or something like that. And it's been very popular, and it has a very unique binary packet signature. So that's kind of why I mentioned it here. There's a few common ways these are leveraged in analysis. So monitoring, so trying to do monitoring, traffic capture. You want to compare it to known threats. You want to do like signature-based detection, all that type of stuff. Another approach that you will use in your analysis is trying to either simulate network services or even interact with the malware. So trying to actually send commands directly to the malware. Again, getting back to the beginning of the lecture, I mentioned most of the time when you're dealing with a malware sample, you only have half the story. You have the client-side infection or client-side intrusion that was delivered to the target, but the adversaries do like to keep the controller under wraps. They like to keep that concealed from public view. So if you want to try and learn more about the malware, sometimes you actually have to do some static analysis, figure out what the command language is, and we discussed doing some of that stuff in the one of the lectures. We were kind of building a Yara signature out of some of the observed strings that we saw. And I made the remark that some of the strings looked like they would be commands and responses that a user would, or I should say an operator would send, and that operator would then see on their screen. So taking that static analysis knowledge and then trying to let the malware connect to, say, a simulated or faked network that then gives you the ability to enter those commands and see what the result is another analysis tactic that'll be used. So, and then finally, I kind of gave some higher level resources and concepts that were existing in the operating system, but also malware itself is an application running within your operating system, and there's also a number of other applications that will be running in that environment as well that themselves have useful information. So a great example would be your web browser that has all your current session information and your cookies, things like that. There's ways to communicate with the other running applications. Likewise, there's also ways to communicate and interoperate with operating system internals that might provide you extra benefit. When you interact with these things, you basically have to make a request and sometimes even create data structure instances in Windows. You have to call a function call that instantiates some data structure instances within Windows to allocate resources. So you get some examples here of ones that you may see, and some of them you may actually be familiar with them from operating systems class or from Unix system, that type of thing. So like system pipes for possibly doing inter-process communication, that type of thing. That ends up being very common with malware that consists of multiple programs. So sometimes there's malware applications that are multiple programs that have to run on the system, and they have to intercommunicate somehow. Mutex is another one that's commonly used, so that if an attacker maybe tries to attack you 5 times because they want to attack you with 5 different exploits, hoping that at least one of them works, they'll make sure that the malware they're delivering allocates a system-wide mutex or mutual exclusion lock that then they can test for before running the malware to determine if the system's already compromised or not. That's their way of trying to do a little bit of workload management on their side. They don't want to have 5 backdoors coming from your system that then they have to deal with. And they also don't want to cause the impact of running 5 extra applications on your system would, because then that would make you more likely to take the action to try and fix your computer, so to speak. So semaphores, similar concept there. Listening network sockets. So with the Metasploit example that I gave earlier, we delivered a program to a user system that initiated a connection from that computer back to a network service that we had listening on our server. It's not uncommon to go in the reverse direction, which is I email backdoors to 100 targets, and then when they run them, those backdoors actually open up a network port or a network listener on the machine and wait for incoming connections. So that's not a really uncommon approach either. And then finally, lock files and things like that. So trying to do resource negotiation with lock files can also be quite common, especially if it's trying to negotiate access with another program on the system. So I think that's all these slides. I'll go and kind of poke around some of these different areas on a Windows system. So I'll go and load this Windows 7 system up, just because it tends to be a newer environment and everything. And so this is pulled from that IE test drive thing that we had. So let's see. The file system ends up basically being this stuff. One of the useful things here is that, for instance, I can go in here and I can look at the properties to get kind of a window into what is available on the, or I should say what's written on the hard disk. etc. I have like quota and sharing and all that stuff. But also, I can go and browse in here, and I can look at, you know, all the different files that are in here. So I'm going to go in like Windows directory, and then, or actually I'll go to users, and then I'll look at, say, like my users directory. One of the things that I can see in here that I need to keep in mind is that by default, I believe that the file listing from this folder is actually filtered to some extent. So I can actually go in here and let me see if I can read it. It's not here. It is view properties, and then I go to advanced maybe. I can't remember how to look for it on here now. I thought it was like folder options. Okay, well I can't see it. Anyway, basically you can navigate all the files in here. I was going to try and show that there is the possibility for some of these files to be hidden from view. For whatever reason, I can't actually. I think I have to go into the control panel and change it, except it used to be a feature that I had available on the drop-down menu in the Explorer. But what I can do is I can actually use the command line, which is going to be more similar to what the adversary is going to use if they're trying to accomplish the same goal. So I can go and get the same file listing just using dir here. But if I want to, I can actually look for files that have certain attributes. So for instance, I can look for hidden files and system files, reparse points, whatever those are. So I can actually look for all the hidden files that are in here, and you'll see that there's a whole bunch of other things like ntuser.dat, ntuser.dat.log1, .log2, all these things. I have no idea what these are for, but looks like they're just folder linkages as well. So it looks like they're links between, so in this case, this one says recent is actually a link to IE user app data, roaming, Microsoft Windows recent, like that type of stuff. Also, I can look in here at the system files, which looks like it's about the same list, but that's just because these happen to be hidden and system files. So Windows embeds all of this information that I'm kind of messing with here to show you in that directory that I was telling you. So when I'm just kind of navigating the system to try and find a file here, I could, for instance, here, I can just do it right now. I could, for instance, create a new text file. Right? And then I can use dir to look for it, and there it is, test.text.text. And then, if I wanted to, I can use a trib to try and hide it. now, well, I don't know why it's still there, but whatever. Oh, because it's S, it's system. So I actually have to do, I have to do this. And then now it's gone, but it's still there. So if I do dir/as or whoops /ah, you can see the file's still there. So using some of the tools that allows you to navigate this directory structure is very helpful in that regard. To be able to get kind of this entire hierarchy listing of what's going on without having to navigate through folders and run these commands on the command line. The other thing that's really common, and I'll go over here to get to it, is so in the administrative tools in the control panel, it actually manages the system services. So if I load this up, and this is kind of what I was talking about, I get a inventory of all of the different drivers, or a whole bunch of the different drivers and like services and frameworks that exist for me to use in the system. And you can see that maybe about 25% of them on this screen right here are actually loaded. I can scroll down here and maybe somewhere around half or less than half on each pane are actually loaded up, which means that the status right here says they're started. That means that me as a normal user am not used to having whatever functionality is offered by any of these things. So from my perspective as a user, like I was actually unaware that any of these were actually installed on here in the first place. So me as a user, a really good example might be like Bluetooth, right? Most people's systems may come with Bluetooth disabled by default. And then it's kind of up to those people to actually enable it. If I never use anything with my laptop that uses Bluetooth, then if my Bluetooth service ends up getting hijacked, and I'll show you, if we go to properties, I can show you it, what I'm talking about, which is, let's see, not entirely certain if it even is going to show it all in here. Yeah, here we go. So this thing right here, so what I've highlighted right there, that's actually a command that's embedded within the Windows registry, so the system-wide configuration that says that when you run Bluetooth support service, right, it actually wants it to run this command. And if I was an attacker, I might actually go into the registry, change this command around, put my backdoor in there, and then start this service up. Set the startup type to be like automatic, like that. Then you, as a user, when you're browsing through this, if you were trying to inspect your system to see if anything was out of place, so to speak, you might go through this, you might see Bluetooth support services actually started. You probably wouldn't have even known that it was turned off when your computer was shipped to you unless you did like an exhaustive review of this whole thing. So looking for those types of configuration changes also is extremely important in identifying when attackers may have gotten in or not. Because for instance, like, these two things, I have no idea what these do, but they're running on here. I have no idea why this is running and this isn't running. So if this happened to be running, tomorrow, I wouldn't notice. So likewise with like any, here's some of the built-in remote access stuff too. So I have these things turned off, of course, on this VM. But the functionality is there to provide like more interactive remote access with the system if someone can just turn that on my computer as well. So, So that's the services, and then let's see, a little bit of time left. I can go in here and come on. So there's also this program that's called regedit or regedit, whatever you want to call it, which is the as I said, that Windows registry is a large database that's always running in the background on Windows. And here's an example of that user account control, so UAC, user account control dialog box, which says, I'm about to do something that is going to give me privileged access to some aspect of my system. The security settings that I have on this VM have been set up in such a way so that anytime a program wants to do that, it actually gives me this box to warn me and give me a chance to deny it. Whether or not this is shown is actually a configuration change that exists and that you can modify. So I can go into details about it. It tells me where the program is and all that stuff. So I'll click yes because I'm the one who opened it. And then this allows me to go and browse either like system-wide configurations that are in this tree. And this works very similar to some of you may have used like Microsoft Access or something like that, or have used the database navigator, database viewer that's built into Visual Studio. This works in a very similar manner. I'm providing you with trees that allow you to see, like I can go in here and I don't know, go down here to Windows, and then Windows has, I'm kind of going through some of these things by memory here, but like audio, enable capture monitor, enable login, log on HID controls. These are both set to true. I can turn those to false, and then when I reboot, whatever functionality relies upon the setting of these things, its behavior will change. One of the fun ones that's in here is if I browse through this, and it shows you right here at the bottom of the window. So right here, it shows you the navigation tree. And this is structured very similar in semantics to like a file system tree. It shows you where you're at. So this one is one of my favorite ones because it allows you to create, say, some arbitrary like notepad, and then I can go and edit this, and I can say, let me see if I can remember where notepad is. Great, C Windows. So for instance, I can do that. And now Notepad may run when I reboot. I don't know. Let's see if I did it right. I just kind of like did it from memory. I can't remember exactly if there's any other parameters that I have to put in there. Or even if Notepad runs as the user I'm going to log in as. So, but you can run like arbitrary programs that way. See, now Notepad comes on when I boot up. So if I'm an attacker, a really easy way for me to get my backdoor to start up on reboot is for me to just do what I just did, which is go to that registry path and then create a new entry in there that says my backdoor